Good afternoon. You hear me?
Yep.
Thank you. Thank you for the response.
You're welcome.
Very good, very good. So let me pull out my chat box so I can monitor anybody with any questions. So I'm going to share my screen. So I want to welcome everybody to the week number 5, lecture B. And we are Friday afternoon again. So I'm now standing between you and your weekend. All right, so let's recall what we did last week, last lecture. We actually went through a lot of things. We can move a little bit quickly, and we are going to continue. So basically, let me show video panel. Okay, here. Basically, for continuous time signal, we need to do time domain analysis. We also need to do frequency domain analysis. Okay, so we need to get used to these two domains. Okay, so for the time domain, we start with what is signal, what is system. Signal is a signal, a system is a system. A system is a mapping between two signals. Okay, so you operate on an input signal, you produce an output signal. So, well, Laplace transform, and we are going to do a CUPI today. So we're going to see. So this is our starting point, and we mentioned about, let me hide this one. We mentioned about a very important name is called Heaviside, okay, Heaviside. And he used the notation rho as an operator, okay? So we can turn a differential equation into algebraic equation. But later on, everything is formalized in the definition of Laplace transform, okay? Laplace transform. So this is Laplace transform. I gave explicit warning about the 0 minus, okay? We should not ignore that, okay? And this is a differentiation law for the Laplace transform, okay? So you should use the 0 minus, okay? So this is a Laplace transformation table usually we are going to give to you, okay? And we even did a simple derivation for when the unit step is 1 and how we can get 1 over s. So step 1 over s, okay? So 1 over s is also called integration, okay? Integrator. So why 1 is connected to the integrator? Yeah, probably we need to think about it, okay? Think about it. All right, so then we have a property table talking about linear combination. We went through derivative law, or if you have high order derivatives, you need to have k minus 1's derivative, okay, for the initial conditions. Integral law is relatively simple. And we also talked about initial value theorem here, initial value theorem here, initial value theorem versus final value theorem. So both here, I want to highlight, don't ever lose this S, okay? Okay. All right. Well, today's quiz is basically to ask you to get training on this entry. On this entry. If you don't note this entry, you will be wrong. Next lecture, I'm going to run through the quiz with you to see why you get an error, why you mess up with this sign, okay? Plus versus you become minus. We're going to work on that later, next week, to review that. But today we are going to continue. So also went through the ABCD part, one thing is clear. So this, for giving ABCD is unique. You can get GFS. From GFS to ABCD is not unique. Therefore, giving a GFS, you have infinitely many possible state space realizations. So just review. And we talked about the transport delay versus delay, how this in the digital computer, they use an array, first in, last out array to represent delay. Okay. Then we talked about first order plus delay time model to mimic this type of temperature control system. Okay, so your temperature sensor and your real process may have a delay. Okay, and I mentioned that among all the industrial applications or the control tasks, among all those control tasks, 80% of the control tasks are for temperature control tasks like this. So therefore, first order plus delay is a very fundamental model. So we should pay special attention to that. Okay. So transfer function is in and out for linear system in algebraic form. We talked about stability, that the poles must be all in the left half plane, okay, left half plane. And we also talked about zeros in the right, on the left half plane. That's giving you a non-minimum phase, 0, okay, non-minimum phase, 0. So, so then we talked about a delta function. That's a unit delta, okay, unit delta. We talked about step response, steady state, talked about direct current gain, DC gain. And in many cases, we make the DC gain as 0. So you have a 1 in steady state, you also get a 1, okay? There's a DC gain. But for transient, so you have 5 parameters: steady state, rise time, overshoot, undershoot, and settling time. So like we showed in this figure, okay? So that undershoot part is due to the non-minimum phase phenomenon, okay? So I hope you pay attention to that. But in reality, you don't have this one. Say, for example, first order plus delay system. You will never have this kind of undershoot there at all, okay? So your input is always like this. So you have T, so you have a L in here. So everything is 0 until L. Then you have something going up. So this is the step response, okay? Step response. And this step response is also called reaction curve, reaction curve. So clearly, if you have a reaction curve, you should be able to infer what's this. This is a part of our homework problem. So giving the measurements, like this figure, you have measurements. Can you figure out what is my T, what is my K, what is my L? So that process is called system ID, okay? ID stands for identification, like you have driver's ID, right? So identification, okay? You identify the system model parameters. We'll see if we get enough time to cover some of the system ID problem, okay? Because we usually start by saying, hey, giving a GFS, this is the things we want to control, but where do you get this GFS, okay? So in reality, you're not going to be giving GFS to start a work. You probably start with Like you are allowed to give a step to the system to see how the system reacts. So then you got a reaction curve. Then you figure out what is your G. Then you start to design the control system. So, but when we see non-minimum phase, that means you have some zeros living on the right half plane. You have zeros, so pose and the zeros. We talked about systems, how you can get into the MATLAB. So you have TF, you have ZPK, you have also SS. Okay, there are actually there are more. I think that there are also like empirical frequency response. Okay, it's something like a FRF, frequency response function. Okay. If you help TF, they will refer you to ZPK and SS and frequency response data. Oh, sorry, FRD. I think they use FRD, frequency response data. Okay. We're going to talk about what is a frequency response today, briefly. We covered what is a relative degree, that is a denominator, numerator. So then the highest degrees, the difference is called relative degree. Okay, relative degree. So usually n is greater than m, okay, usually. But sometimes n is m, okay, n is m. But in practice, this is usually true. You don't have n is m. We'll emphasize this, okay? We'll emphasize this in a minute. So pose, you may have repeated pose, you may have a complex conjugate pose, you may have a distinctive real pose, and so on and so forth, okay? So in this case, we have very single pole, okay? Have this one. So, so I want to see what's the step response. So this is a step, this is a system. So step response, there's a key step here. You should have learned this thing in high school. It's called partial fraction expansion. Partial fraction expansion. And you write, it turns out it's like this. So after you get this partial fractions, then you can use lookup table. You can get this response. So this response, in principle, I will say this is wrong. You should put the comma t greater than or equals to 0, okay? Because if it is t is a negative, this is not going to be right, right? Can we get the attention on the lab? Could be. Let me check with our TAs. You mean the lab 3? I think it's due on the next Friday, right? Not today. Or lab 2? Are you talking about lab 2? You should have enough time, like a week window to finish. So we're going to do a CUPI today. So, okay. So this is a step response for the first order system. So, all right. So this is called steady state value, y infinity, okay, y infinity. So there is a magic number here, 632. Why this is the case? Yeah, you should be able to figure out that. So because that is 1 minus et minus tau, okay? When t equals tau, so this is something 1 minus would be nice if it is due Sundays. Okay, good suggestion. I'll ask them. Okay. So this is due to that. So then you have a 1 minus e minus 1. Okay. So this is like 33.2%. Okay. But anyway, there's another way you can do. You do a tangent from beginning. You do a tangent sloping here. This slope hit this point, then you do this one, then you get this tau. So, but today this is a graphical approach. Today you can use computers to fit it using a least square fitting. Okay. So what do you mean facts, Emmanuel? Did I miss anything? Okay. Okay, I didn't get that. So now I get it. Okay, good. Thank you for teaching me about facts. Okay. So let's continue. So we cannot stop at the first order system. We should also talk about second order system. So when the second order system, you have three cases. One is you have a one pole with the case one is like s plus a square, like a square. Why I keep writing this? Because we can see here h0 is 1. Do you see h0 is 1? And this one is also h0 is 1, right? So the DC gain. So I write this way. Do you see that? So this is a case 1. The case 2 is you have a complex number like s plus c, s plus c complex conjugate. So you have a c square, right? So that's DC gain is 1, right? Do you know what I'm writing? C is, say for example, is so this imaginary of c plus imaginary c times I plus real part of c, right? Then c minus is minus imaginary of c, I plus real part of c, right? So this is a complex conjugate, okay? So this is one part, okay? So there's two cases here. So the reason we put a canonic in here is because this one is cancel out to give you the DC gain is 1. Another one is to put this coefficient as 2 phi omega n, okay, 2 phi omega n. So this omega n has a name is called natural frequency. This phi has a name is called damping ratio, okay, damping ratio. So it could be that damping ratio is 0, okay, it's 0. And the damping ratio could be 1. If it is 1, then you have a complete square like this one. This is damping ratio phi is 1. Okay. And of course, the phi is 0, it will become like this. Okay. And in this case, they don't have a real part because this is a purely imaginary part. Okay. Okay, so we're going to continue. Okay, that extension, don't worry. We'll work on with my TS and let you know. Most likely we'll give you the extension. Okay. So if you put this as a system h of s in here, and you put 1 of s in here, then you have y of s. Then you do a Laplace inverse Laplace transform, This one, you are going to get a y of t. This is called canonic second order system step response. And it will give you this complicated forms. And I don't expect you to really do this. However, you should be able to figure out what's going on. You do a complete square, okay? Because you have S plus 2 phi omega and S plus something, right? Plus omega n. Let's assume that I have a phi square omega n square and plus or minus phi square omega n square. I borrow one, okay? So then I can do a complete square here. So what is this one? This one is nothing but omega n square minus phi square omega n square, right? Make sense? So I borrowed the one to give to you. So, okay. So you know what is the omega d, right? Omega d. So you write the complete square form, and you make sure you understand here. So you have you put this product form. You have a 1 over s times this one. You product form. You make it PFE form. Okay, PFE form. So then PFE form, if you combine all the denominator together, you'll get the same form like this one here, okay? So no problem. So after that, you can do a lookup table to check what is your time domain signal. Then you combine everything. So this is one, okay? I think it's a good habit to always write this one. This is true for t greater than or equals to 0. It may not be true when t less than 0, okay? That's according to the Laplace transform, okay? Because otherwise, when t less than 0, this term will blow up to infinity, which is not true in the physics. So, make sense? All right. So you can see this is called a damped sinusoid, okay? Damped sinusoid. So it becomes all the coefficients are connected. There's a dedicated formula, okay, for this canonic second order case, okay, in our Mechatronics Foundation textbook. So 0 here, we have talked about it, and we have seen different examples. When S written in that way and divided by C in here to cancel out. So again, this DC gain is 1 is to be easy to see because this end up in here is 1. You give me a 1, I give you also 1 eventually after settling the transient. But the transient behavior is different. Transient behavior is different. When the C direction is different, okay? When C different. So when C is when the 0 living on the right half plane, okay? So we call this non-minimum 0, okay? Non-minimum 0. Non-minimum phase 0, okay? Non-minimum phase 0. So regarding why this is called non-minimum phase, we can do that in later part, okay? Later part. When we learned body plots, okay? So there are some important consequences of the zeros on step response, okay? So you can see when you have a right half plane zeros, you have this behavior is called undershoot, okay? Undershoot. So there are some very interesting analytical results, okay? So let's assume that you have a corresponding time function like this. So this is your Laplace transform. So if you put a weighted, this is a Z0, will give you a, this is like a pole, okay? A strictly proper function of Laplace variable S with a region of convergence with greater than alpha. Time function H, Laplace transform is capital H. So what do we call? It's called a Laplace transformation pair, okay? Pair. So in this case, we do a Laplace transform, then it's exactly, we put S goes to Z, 0, like this one. This is Laplace transform. If I put S in here, okay, then it's H of S. Okay, but now S is 0, okay? S is 0, okay? So then it's exactly like this. So this is according to the definition, we just send S to 0, we are going to get it, okay? So that's simple, that's simple. However, you have a linear stable system of the H of S. If you have a unity DC gain, okay, unity DC gain, what does that mean? H0 is 0, sorry, it's 1, it's 1. And if we have a 0 at C, okay, 0 at C, and C is on the right half plane, so this is our HP, so right half plane, living on the right half plane, it's already non-minimum phase, see that. Then we assume that the unit response you have a Y, you have certain time T of S, okay, okay. So we can see that the Y will be in between 1 plus delta and 1 minus delta, okay, in between that. So then you will have an undershoot for sure, cannot be less than, they have a minimum bound. So this is the bound, okay, this is the bound, okay. So it's not avoidable, okay, it's not avoidable. And this is linked to how big is your C, okay? C is here, okay? Your 0 position, how far away from the imaginary axis. So that minimum bound is an indication that it's not avoidable. It's not avoidable, okay? So if you have a non-minimum phase 0, you have a 0 living on the right half plane, then there is a trade-off between having a fast step response and having a small undershoot. So in other words, if you want to go faster, okay, you go faster, then you have, so you go faster, you will do something like this. So if you want to go faster, you have a bigger undershoot, okay? All right, so it's a conflicting requirements. You have faster response, you may have a larger undershoot, okay, undershoot. So you have a slow 0 and overshoot. So this is something you don't have to memorize. You just to know the consequence of having a 0 C living in a right half plane. What's the consequence? Okay, what's the consequence? Again, if we assume that this H has a unity DC gain, you have a 0 at C, and C now is less than 0, is on the right hand, is on the left half plane, which is good. So then you do, this is the arrow, okay? 1 minus Y is your arrow, okay? Because your Y infinity is supposed to be supposed to be 1, okay? Everything else is transient. So this is like a reference, minus this one is the arrow. So this VT, okay, the system has a dominant pole with a real part, which is also on the left half plane, okay, left half plane, because it's a minus P, okay. So then you have 0 and the pole, you have a related, so your 0 is smaller than pole. In other words, if you draw this one here, so pole is here, 0 is here. So that satisfies this eta less than 1, okay? Eta less than 1, okay? Okay. but you should have the ratio is as big as small as possible. So that means this is relative closer to the imaginary axis, and this is far away from axis. Okay, so if this is true, then we further assume that settling time. Okay, the settling time you have. I have said you have 2% or 5%. Okay, so this is delta here. So this is the delta, remember? The delta. So it could be 2% or up to 5%, okay? Doesn't matter. You can say I'm 3% away. It's okay. So that delta, okay, decides your settling time, okay? Settling time. So what I'm trying to say is the arrow, okay? The arrow can be upper bounded by this. So the arrow is, so you have something like this. So this is your response. This is your y. What is your arrow then? So the arrow is 1 minus y. It will get you what? So initially it's 1. So initially is 1. This arrow is 1. So it becomes like this. So it goes to 0 here. So this is t. Okay. So this is the what we call the v. Okay, v of t. So the magnitude of v of t is bounded by this. So bounded by this one, when t is 0, then this is k. So bounded by something called, here you have k, and you have something bounded below this curve. Okay, below this curve. Okay. So this is all very interesting quantitative behavior. Okay, quantitative behavior. Okay, so that's enough for discussing about the consequences of having a 0 in the right half plane and left half plane. Left half plane depends on the ratio. So this ratio need to be observed. Okay, need to be observed. This eta. Okay. So today we are going to talk about frequency response, and we are going to run through the basic ideas. And but before that, okay. So thank you. Yeah, I'm going to talk to the T after the class. Okay. So if we assume that we give sinusoids to the system, okay, the system is h of s, so it's h of s, okay. So we'll give you sinusoids. So then this h of s is actually called linear time invariant system. So then you are going to have a sinusoid out. So sinusoid in, sinusoid out, but with different amplitude, same omega, sine omega, right? Same frequency, but with different amplitude and different phase. And the difference is linked to the omega, okay? So this is my output in time domain. It's written also is a sinusoid, okay? It's also sinusoid of the same, this is a sine omega t, okay? Sine omega t. So again, for frequency response, we're talking is I have sine omega t injected into the system to see what's the outcome when the transients are die out. Okay. So in a steady state, then your output is also a sinusoid. So the rule of thumb is sinusoid in, sinusoid out, same frequency with two differences. One is different amplitude and different phase. And the amplitude and the phase, okay, amplitude and phase will form a complex number. So this is amplitude, this is phase. And both amplitude and phase are frequency dependent. It's a function of omega. So your omega changes, then this phase and magnitude also change, okay? And interestingly, we simply put this transfer function, replace S with j omega, then we can get a complex number in here and write in the magnitude and the phase form, okay? So for example, in the end, you can do a plus j and times b, right? This is a complex number. So you know how to write, this is a real part, imaginary part. Then you can always write a magnitude and ej theta format. So this is called magnitude polar form, right? It's called polar form. Magnitude phase format, okay? Okay, so then we try to draw two pictures. One is magnitude of h, this guy, to draw this guy versus omega, and draw phi omega versus omega. So both of these together are called frequency response, okay, of the system, this system here. So I hope you understand we are not just talking about changes over time, how the system behaves. We are talking about how the system will behave as my omega changes, as my frequency changes. So that's why we call frequency response. Well, what is the y? Y is called time domain response, okay? So then you draw the two plots, this one versus omega, this one versus omega, are called frequency response, okay? So is that clear? Don't get confused. All right, so summary, summary in words, okay? If I want you to write down what is the basic idea of frequency response, you should say that you have a sinusoid wave input. You forces a sinusoid wave at the output with the same frequency, okay? However, that output frequency signal has a different amplitude. Output of the amplitude of the sine wave is modified by a factor that is equal to the magnitude of hj omega, okay? H is my transfer function. Phase is shifted by a quantity equal to the phase of the hj omega. Hj omega is, so then you will be able to draw two plots. So one is hj omega, put its magnitude versus omega, okay? And you also could put the phase. So this is omega. So this is we usually use phase like this, okay? And usually is in degree, but this is a magnitude. You can do 20 log 10. So turn this one to dB, and usually you use this one's log 10 omega and log 10 omega. By doing that, these two plots are called body plots. Today, we are not going to learn how to draw body plots. We are going to learn next week. But today, we are going to spend some time on the quantitative behavior, okay? You got a feeling about the system behavior in both time domain and frequency domain. So the board diagram, I already explained to you, okay? So we are going to study how to draw it next time, okay? The next time. So, but there is something called decade. Decade means if you have omega here, then you have 10 times the distance between this one to here is called a decade. Okay, 10 times. Okay, we are going to talk about this one later. Not this one here. We are not going to do this one here. But I'm interested in learning how to do. You have this one, okay? I'm interested in learning how to do, so I give you, this is a system, I give you a step, okay? And what is, okay? What is your output here, okay? Output here, well, what is that? How to solve that, okay? Do you guys have an idea? So it is not easy. Say, for example, if I write this way, so basically I have 1 of s in here times this thing. So I have 1 of s times this one. So then I need to write like 1 of s plus s plus 4. So you have I don't know what's this value here. Let's say this is a K1, it's K2, plus K3, S plus 8, plus K4, S plus 10. Okay, so the question is how I solve this K1, K2, K3, K4. You can do the brute force way. That is, you use common denominator. This common denominator is S plus 4, S8, S plus 10. Then you do the expansion of this one, and then you combine and you put all the coefficients together. In the end, you can write a very complicated form in the numerator with a K1, K2, K3. Then you compare term by term. So you will get 4 equations, okay? By comparing, the numerator is 640 times S plus 640, okay? So you also have 0 times S squared plus 0 S3, okay? S3, as well as 0 S4. You don't have S4, do you? No, you don't have S4. You only have S3. Okay. Okay. So you compare this one with another one. You do using common denominator. So you have 4 simultaneous equations, like K1, K2, K3, K4. You do this stuff. This is very tedious to do by hand, okay? So I want you to learn today a technique that is called CUPI, okay? CUPI. Called cover up and plug in. So you can see what are the distinctive roots. You have 0, you have -4, -8. Listen carefully, okay? -10, right? These are your roots, right? They're roots. So this whole process is called PFE. You need to know this thing, you know, you have to learn this. You don't want to use brute force way to solve this 4x4 matrix equation. It's very difficult. We don't want the brute force. By identity, you know, compare the coefficients. So you get 1 equals 0, another equals 0, another one equals this, and you don't want to do that, okay? This is too tedious, okay? So you have to borrow the other idea, like here I'm using called CUPI, okay, called CUPI. So how can I get K1? How I can get K1, okay? So the K1 is you cover this S. You cover, so because we have this one is S times, so we have this 4, right? We have 4 terms. S plus 4, S plus 8, S plus 10. We have 4 terms, remember? I cover one of them. If I want to do the K1, I cover S. So I cover this guy. I cover this guy. So I only have this left, okay? So then I plug in what? Plug in the one you covered corresponding to the root, the pole is 0. So then I plug in the everything left here, everything left in here. I plug in 0. So 1, this is 4, this is 8, this is 10. So 10, you can cancel this 64. So you see that is 640 divided by 4 times 8 times 10. That will give you cancel 0, you get 8. This is 8, 8 is 64, 8 divided by 4. So this is 2. So this guy should be 2. Okay, this guy should be 2. K1 should be 2. Okay, this is K1. Okay, but what is K2? So what you should do is you cover this term, okay? What's left is, then you plug in -4. So what you get is 640 times plus -4 plus 1 is -3, right? So in the numerator. Denominator, you have -4, S is -4, plug in. And because S plus 4 is already covered, so then you have left is 4 minus 4 plus 8 is 4. Minus 4 plus 10 is 6. So if I do some change, so you have minus minus, so then everything should be positive. Okay, so then you further do this one, well, and this one is 2. Okay, 2 times 8 is 8. 8 is 80, right? So this is 80. 80 divided by 4 is 20. So K2 should be 20. Okay, K2 should be 20. So cover up and plug in. Okay, cover up and plug in. All right. Cover up and plug in. So let's do the next one is cover up S plus 8. Then I have a plug in S equals -8. So 640 times -8 plus 4. But -8 plus 1 is -7. Okay. Then you have a -8. S is a -8. Then you have a -4. Is -8 plus 4 is -4. Then you have a -8 plus 10 is -2, right? -2. So what are you going to counting how many negatives? 1, 2, 3, 4. So everything is positive, right? Everything should be positive. You have 4 of them. So the K3 should be positive. So then I can ignore the negative signs. So this one will get you 80. 80 divided by, so you got divided by 8 is 10. 10 times 7 is 70. So K3 is 70. Okay. So what is K4? Okay. So K4 is you cover S plus 10, you insert -10. So in the numerator, you have 640 times -9. So you have -10 is first one. The second one is -6. And you have a -2. Because you cover S plus 10, okay? So then we are going to get, so you got 10, so again, this is positive because you have 4 negative signs. So then you cancel this one is this. So you do 3, then you get a 2, you get a 3. So you get a 4, so divided by 4. So 1 divided by 4 is 18, right? Oh, no. Is that right? divided by 4, 16, sorry. 16. 16, okay. 64 divided by 4 is 16, okay. So the whole thing will be 48, right? Yeah, times. So I got this K2 is 20. And this is 70. And this is 48. So if I give you a polynomial like this, h of s, you should be able to do this coefficients PFE via the CUPI method. I worked with you one by one. Okay. So then after that, so you should not write what I'm doing here. So you should write Laplace inverse transform of this one. Okay. So then in the end, what you should do? So what's your YT? YT is 2 E, no, it's just 2. S 2 divided by S is just 2, right? K2 is 20, E minus 4T, right? Plus 70, E minus 8T, plus 48, E minus 10T. Is this correct? No, if you don't write this one. So when T greater than 0, because T is negative, then you have something divergent, right? So this whole thing is what we have. Okay, what we have. Of course, you now learn how to do this step response by using a step, by putting this thing into your system in the MATLAB. But you don't really have to expand this one, right? So there's a ZPK you can use, right? Have you used that before? So the CUPI, of course, is much faster, much quicker, and it's not easy to make errors. So you should learn this method called CUPI, cover up and plug in. But this is only valid for distinctive roots. If you have like a s plus 8 square, then things will be different. Yeah, but this trick is important. You should learn. Okay, so you can get a YT immediately. It doesn't matter you have a very long, many of the roots, you can still do the same idea. You know this CUPI? So let me do this one back. We have seen a system here, but we didn't mention this is CUPI to you yet. So let's do CUPI here. Okay, so let's do CUPI here. So what we get is a K S tau S plus 1. But this is better to written in terms of K divided by tau S plus 1 over tau, right? You better write this. So then I'm going to do CUPI. So I want to do like this is a K1 divided by S plus K2 divided by S plus minus tau. So to get K1, so I cover up S, right? This is my K1. I cover up my S here, then insert S is 0. So the K1 should be copy K divided by tau here. Then you insert cover S, you insert S to 0. So it's 1 over tau in here. So what you get is K. So this is the guy K, right? So how to get a K2? So let's do the trick. The K2 equals cover up this S plus 1 over tau. You insert, okay, insert S is minus 1 over, so you should insert minus 1 over tau. So it becomes K divided by tau, copy. And I insert S is minus, so the root is minus, wait. I touched something, I guess. No, that's all. Here. Do you guys know the root is 1 over tau? S is 1 over tau, minus 1 over tau. Because S is minus 1 over tau, so this is minus K. So that's what. Oh, wait. Oh, yeah. It's 1 over K. So it's correct. So it should be K minus K divided by S plus 1 over tau. Okay, so this is the second term. But if you multiply tau back again, so you get a tau in here, you have 1 in here, right? So it's the same. Is this magic? Yeah, you should learn how to do this. So with CUPI, we can also do that. So this is more systematic. So you have 2 roots, one is 0, one is minus 1 over tau, okay? So actually we can do evaluation here. We can do evaluation here to see whether this y of t is the same as my here step of the h. Okay, so you guys can try. We should not use too much of the time here. Okay, so I'm leaving the body plot for the next time. Then we talked about filtering and so Fourier transformation. Do you guys learn that Fourier transformation and Laplace transformation are in a similar form in the sense that you put S's j omega in here. However, Fourier transforms is from minus to infinity, okay? And this F versus F is a Fourier transformation pair, right? Okay. So then inverse is like that. So this is also mentioned in our textbook as well. Okay. So then you can see there's a Fourier transformation table. You also have Fourier transformation properties. I believe they are parallel to the Laplace transform. Okay. One of the interesting thing is you have so if you have a signal you integrate them together. Okay, so you are going to have the same form like that. So imagine that. Okay, imagine that this G is also F. Okay, so F times F. Let's say the F is a scalar. F times F is F squared, right? I told you F squared is what? Is power, right? It's proportional to the power, right? Then you integrate all the power together, what do you have? Energy, okay? So you can see this is the energy expressed in time domain or the energy expressed in frequency domain. So this conserve, okay? So this is called Passivhaus theorem, okay? So this is our last slide. We're going to spend time on it. So after that, we are not going to add more things into our today's time frequency domain. Today, we mainly focus on the CUPI technique, okay? This is, this is a system. So you have first order system. So we are going to try to increase the K. So you can see increase the K, the final value is different. So this is a T, this is a Y. So usually you have a step in here, okay, step response, and then what is your Y? So we're trying to see if I give this system a step, then the bigger the K, and then the bigger the Y infinity, right? If you do not change k, so your y infinity will be the same. But if you change the tau, when you reduce the tau, you increase the tau, okay? Increase the tau, okay? You increase the tau, the system actually goes slower, okay? If you decrease the tau, it's going faster. Why? Because the system is proportional to like e minus t divided by tau. So when you have a tau bigger, okay, so then this whole coefficient is smaller, so it's slower. In other words, you can also check, okay, or check in the real and imaginary part. So you have a pole, which is 1 over tau. This is 1 over tau. So when you have a tau go this way, that means tau is going up. That means you are going, tau goes up, you are going towards the imaginary axis. Okay, so means if you are closer to the imaginary axis, you are slower response. If you are leaving far away from the, say for example, if you are here, okay, so it will be much faster to go up, okay, to go up. All right, okay. So I hope you get a sense, but for the body plot, we don't talk about it. Let's only look at this one, okay? Look at this one. So this is the first order system, okay? So this is the second order system. You have seen this one before. So this is omega n, okay? This is omega n, they lost n. So they write this is a canonic form. The canonic form, this DC gain is 1, okay? In other words, you always, but this one, K goes up because the DC gain is no longer 1. DC gain is K, okay? DC gain is K. So here, DC gain is 1, okay? If I keep the omega n as a constant, we start to change the omega, change the phi is a damping ratio. So I give a step here, it will also get the step is 1, okay? So this is 1, because you give a step, so this is 1. So this is YT, the step response. So you can see when phi goes to small to big, okay? You have a bigger one, okay? Small to big, you have a big one. So then you start to become, when you have very small, okay, very small, say for example, when this guy is 0, when phi is 0, what's going to happen? So you have purely sinusoid without any damping. So this is phi is 0, okay? Because this is s squared plus omega squared, that will give you sinusoid, okay? All right, so then we have phi goes from 0 and bigger, okay, phi and bigger. Then it will start to become a die out until you can see the phi is very big. Then it will be undershoot, okay? So not undershoot, underdamped, okay, versus overdamped. So then this is called overdamped, okay? It's so slow, okay? It's overdamped. So when you have oscillations, it's die out very slowly. It is called lightly damped, okay? Lightly damped, slightly damped. But when you quickly die out, it's called heavily damped. And then when you do not have an overshoot, it's called critically damped or overdamped, okay? Overdamped. So given the phi, and you change omega, then of course, your omega will be, the response frequency is different, okay, different. So that's one of the idea. Next idea is, this is a very interesting example I want to show. So this is, you have a pole at -1, okay? Pole as a -1, but you have multiplicity, okay, 2. So it means to the power of 2. So this is called pole -1 has multiplicity of 2. But in here, you don't have that. So this is called distinctive, or pole has a multiplicity of 1, okay, has 1. So we are going to talk about A. So A is, let's say A is positive, okay? So then I know that my DC gain is 1, okay? This DC gain is 1. It's 1. So this is 1. I know without saying this is 1, this is 1. Without checking, I know it. Okay, step. Unit step. Okay, this is a unit step. Unit step. Okay, so you can see if I change the A, so for this case, this is a minimum phase. So that means if I give you a step, it always follow my direction, go, okay? But with different A, I have a different overshoot. Okay, I have a different overshoot. Increase A might increase my overshoot, okay? But if A is negative, so A is negative, okay? So when A is very small, like 0, so it will go this way. But if A is slightly not 0, then this pole in the this 0 lives in the right half plane. Okay, you can see that as A goes up, means my pole is closer to my imaginary axis. Okay, imaginary axis, because the pole, if you do the pole, the 0 is actually 0 is like this. So here is 1 over A, 1 over A. If we increase the A, that means the 0 goes towards the imaginary axis. Then actually you have a very bad behavior, larger and larger undershoot, larger and larger undershoot. So all this can be verified using a MATLAB Simulink. But this type of qualitative behavior, you should be able to illustrate without using a MATLAB Simulink, okay? Similarly, you should be able to show by simple sketch, and then what's the trend changing over here, okay, over here in the body plot. So next lecture, we are going to learn the body plot. So now giving a transfer function, we should be able to do step response or impulse response, okay? And frequency response, we already had a concept of what does that mean, is how the system change along the time, okay? Along the frequency, along the times, time domain and frequency domain. So, but on the other hand, so giving a system, giving an input, you get output in Laplace transform domain. We should be clearly from now on to think about there is nothing really 100% accurate in terms of model. There's a person, you can Google him. It's called GEP Box. He said the following, okay? All models are wrong. Some of them are useful, okay? So depending on your purpose, you should not pursue 100% accurate model because there isn't a 100% accurate model. So be careful. From now on, we should know that the model always contains some uncertainties, okay? And that uncertainty could be written in this called additive case. Okay, additive case. While this is called multiplicative case. Multiplicative case. Okay, so so in many of the situations, for example, you have time delay. This actually is a very hard transfer function. Actually, it is an infinitely infinite dimensional. Okay, infinite dimensional. So in fact, you can approximate this one using this type of approximation, using a very high order. So just multiply them together. Okay. So some people did this approximations for you, different case. Okay, different case. Okay, to the magnitude. So it's not a very nice. It's not a very nice approximation. I don't like it. Okay, don't like it. So what it should be, because we know that this guy magnitude is always one, no matter what's the omega, right? So this is e to the power of whatever complex number. So the magnitude is one. So look at this. It's no longer one, but it's fluctuating around this. And you call this a good approximation? Nah. So it's not that good. So, well, we are going to finish here. And usually you don't know what is your bound or what is your uncertainty, but perhaps you have a good idea about, you do not know this uncertainty, but perhaps you know the bound, okay, the upper bound, okay. So that's how in industry people discuss this. Oh yeah, it's uncertain, there's something, but you know it can be bounded, upper bounded. So this is also called upper bounded. By another function, or can be frequency dependent. Okay. So two key approaches for linear dynamic system is time domain, frequency domain. Okay, time domain, frequency domain. In the frequency domain, the key part is to do a body plot. And next time we are going to do body plot. In time domain, for step response or impulse response, I think the CUPI is the most important one. Okay, it's the most important one. There are exceptions. Say, for example, if you have a S plus the P1 square, S plus P2, S plus Z1. So what if you have this type of thing? What are you going to do? So this, how you handle this one. We have examples on that, but I don't plan to, I don't want you to memorize this one, okay? How to do this. But still using the CUPI, but with additional rules, okay? We'll see if I have time to cover this multiplicity and more than one case, but we really need to focus on the body plot, okay? I think in time domain, in frequency domain, so we're going to walk you through more next time, okay? So very good. I'm going to check with my TAs regarding the extension, okay? All right. It's due supposed today, and we're asked to extend it to Sunday midnight, right? Yes? Okay. You would help? No, actually it's not. In fact, it will destroy our weekend. So. Okay, have a good weekend. I'll ask them to do that. Extension and for the future labs due on Sunday midnight. Okay. All right. Today we got a 51. That's great. Thank you. And I'm happy about how many students signed up for the synchronous lecture. Bye-bye. Have a busy weekend. Safe weekend also. Bye.